Good afternoon, everybody, and a warm welcome and thank you for joining us on what is our latest webinar on control of static electricity with humidification. My name is Dave Marshall-George, and I'm the UK and Ireland Sales Director for Condair. And with me today is Anthony Hall. Anthony is the Area Sales Manager for Condair. And we expect to have over 400 people with us today from many different countries, so you'll all be on mute during the presentation, and my camera will turn off when we start the presentation so you can concentrate on the slides. And if you have any questions, please submit using the text questions function in the control panel, and Ant will answer some as we go, but then the presentation is finished in about 45 minutes. I'll also be addressing some of the most popular questions before we conclude. I'd like to draw your attention to the 3 documents in the handouts panel, in the control panel. There is the 10-point guide to specifying humidifiers. There's a Condair product range brochure, and there's the copy of the presentation. After the webinar, all attendees will receive a link which you can download and watch the presentation again, and you'll also receive a CPD certificate. So as a brief introduction to Condair, Condair is the largest manufacturer of humidifying control equipment in the world. Our head office is in Pfäffikon in Switzerland, where our R&D is conducted. And then we have 4 manufacturing sites across the world. One in Ottawa in Canada, one in Hamburg, is a European hub, and one in Rouen in northern Denmark, and one in Beijing serving Asia and Australasia. And we've been in business for 75 years this year. And we also have over 27 wholly owned sales and service companies across the world. So we are going to dive in, and my camera is going to be turned off, and the learning objectives for today are understanding static electricity. What is static electricity? Then we're going to look at how we combat static electricity. What do we do to try and get rid of any static charges built up in an object? Then we're going to look at understanding humidity, what humidity has to do with static electricity. Why would we humidify to prevent a static charge? Then we're going to look at humidification systems, both isothermal and adiabatic, and considerations for why we would choose one or the other, and the sorts of pros and cons of choosing those sorts of systems. And then we'll have a look at the process for designing and installing a humidification system and other considerations. So let's firstly look at understanding static. Well, what does Wikipedia say? It's always a pretty good place to start. Static electricity is an imbalance of electric charges within or on the surface of a material, and the charge remains until it's able to move away by electric current or electrical discharge. So often caused by friction when objects come into contact and then separate and then come into contact again. The word static is used to differentiate it from current electricity, where an electric charge flows through an electrical conductor. So in the image here, we can see a girl sitting under a synthetic blanket, and her hair is wildly attracted to the material in the blanket. So how does this happen? Well, when 2 surfaces contact and separate, charges are transferred from one surface to another. And as there's no circuit to allow the charge to leak to Earth, an imbalance of either positive or negative charges occur. And as positive and negative charges attract, this imbalance can lead to an attraction between surfaces or a repulsion. So creating electrostatic charge by contact and separation of material is known as triboelectric charging. And this term is derived by the first recorded observer of static, who is a Greek called Thales of Miletus, who observed that when amber is rubbed, it attracts dust and leaves. So the word triboelectric comes from the Greek word tribo, to rub, and electros, meaning amber, which is the fossilized resin from prehistoric trees. And that's where we get the word for electricity. So triboelectric charging involves the transfer of electrons between materials. The atoms of a material with no charge have an equal number of positive protons in the nucleus and negative electrons orbiting the nucleus. But when two materials are placed in contact and then separated, negatively charged electrons are transferred from the surface of one material to another. And which material loses electrons and which gain electrons will depend on the nature of the two materials. The material that loses electrons becomes positively charged, while the material that gains electrons is negatively charged. So what are the effects of this? Well, we can get attraction and repulsion. If we get an object that is in contact and then separated, contact and separated, and so on, and we get two objects that are one's negatively charged and one is positively charged, there'll be attraction. And here you can see the paper sticking together. Or alternatively, if we get a negative charge and another negative charge, then we'll get repulsion, in the same way as we put a positive charge to a positive charge. And those of you remembering your science sessions at school where you've got magnets, if you put the positive charge together with a negative charge, we can attract the two magnets clinging together. But if we try and put the positive to another positive or the negative to another negative, then we get repulsion. And of course, a huge problem that can occur is when the static gets the opportunity to dissipate into an object. There, we can get a huge voltage transferring, or we can get a spark. So all of these effects, both attraction and repulsion and discharge, can have very negative effects on processes in manufacturing. So if we take printing, for instance, and we mentioned paper already, if we get paper that's being stacked or moving through a machine and coming on into contact with an opposing charged material, then we have the potential for attraction where paper will cling together, but we also have the potential for repulsion, so paper won't stack correctly. And it's not just paper, it could be any material that you're printing on. So it could be PVC, plastic, anything. And in textiles, if we've got a negatively charged and a positively charged fibers, then they will be attracted to each other. And that can then cause technical issues as you're weaving the fabric. And similarly, if you've got negative and negative or positive and positive, you get repulsion, and you can have equally poor results in the quality of your manufacturing, as the fibers don't go through the machine in the correct form. If you have an application where you're conveying, then you've got a potential movement of many different objects. Firstly, the rollers and the conveyor belt. And you may have guide rails along the side of the conveyor. But also you've got the materials that are on the conveyor. That could be coming into contact with side rails, with conveyor belts, with other products on the conveyor. And this contact and separation, again, can lead to a static buildup. And depending on the materials involved, that could be either a positive or negative. And of course, the effect of that is that we get attraction and repulsion, and we also get the potential for a static discharge. So certainly in a conveyor application, if you've got counters or switches or sensors, that can have an effect on the efficiency of that. Packaging, plastics and chemicals. Again, if we've got objects that are in contact and then separating, in contact and separating, then we have that potential for triboelectric charging. And a good example would be in a pharmaceutical application. If we're producing a tablet, let's say there are hundreds, if not thousands of tablets that are being dropped into a blister pack. And if we've got a negative charged pharmaceutical and a negatively charged blister pack, then there will be a repulsion there. And the speed of that process and the quality of that process will be dramatically affected as the tablet doesn't drop into the blister pack correctly. Again, it depends whether it's negative or positive, and the effect will depend on the materials. Surface finishing, again, if you've got fibers that are coming off the sanding deck and are negatively charged and the sanding deck is positively charged, that dust will be attracted back onto the surface, so it will affect the finishing and reduce the quality of the material. Electronics and data centers, well, yeah, with electronics, it's very common to try as much as we can to combat static, and we could have an electrostatic event happening either from a component that comes into contact with another moving component, or indeed a moving component that comes into contact with a stationary component. We could get a static discharge, or indeed we can get a static discharge from an operative that goes into a semiconductor or electrical component. And of course, a tremendous amount of damage can be caused. In data centers, it's very common to put as many systems in place in the data center to reduce the potential for static discharge, because reliability of the servers can be significantly affected. And that's why we see a common set point relative humidity in a data center to be 50% RH. And we'll discuss why that's important shortly. And of course, finally, we know that there is a potential for a spark to happen when those two surfaces come into contact with each other. And of course, a potential catastrophic outcome of that can be a fire or explosion. Because we have a source of ignition. So any application where we've got an environment with anything that's explosive or combustible, then combating static is essential. So that's why static, it builds up in an object, and the sort of applications that we see where it's a problem for us. So what do we do to combat static? What can we put in place? What can we do to ensure that this doesn't happen? Well, there are lots of systems for either removing or preventing static charge buildup, but these systems are typically local. So they're only going to combat static at a single point of contact. So you could have a metal foil tank that you're taking from an area where static is built up and taking it to Earth. Or you could have an air ionization system that is going to blow air and deionized air into the space to allow static to distribute. But again, it's only going to do it in a very localized way. And you can even have anti-static floor paints that will distribute static. But again, it's only going to do it in a very local environment. You've got a large storage space or a large production facility. It's not going to combat static in every area of that space or every part of that machine. There are other ways of combating as well. It's quite common to see electrostatic proof packaging that's there to prevent damage to semiconductors or electrical components. And that's great while it's in transit and it's packaged. But as soon as you remove it from that electrostatic proof packaging, then there's the potential for damage to that component. It's quite common as well to use earth bonding straps for ground operators. So any static charge that builds up in the body or in the item is distributed to earth. But again, there are large limitations for this because for it to be effective, the earth bonding has to be in place and it can only operate in a local environment. Now there are meters that you can buy that can monitor an electrostatic charge, and you can ascertain certain individual points where a static charge builds up, and you can put measures in place. But again, it's only a local solution. It won't combat static over a wide area or a large machine. So this presentation is about using humidity to combat static electricity. And it's a relationship that isn't very often fully understood. Because when we humidify, what we're doing is we are increasing the water content in air. And typically, when we talk about electricity and water, the overarching issue is to keep them separate. And the reason that we keep them separate is water is a very good conductor of electricity. So when we humidify the air, we're increasing the moisture content in the air. And if we increase that moisture content across the static threshold, which is around 45% relative humidity, then that imbalance of electrons that's built up in an object from it coming into contact and then separating, coming in contact and separating, and generating that static charge can use the water molecules in the air to conduct to the earth. So why we would ordinarily separate electricity and water, here again we're using the water molecules in the air to conduct that imbalance of electrons, that is a static charge, safely to earth, so it doesn't discharge into an object and cause attraction, repulsion, or sparking or a source of ignition. So for a lot of applications, it's critical that we humidify. And the data that we can see in this table here demonstrates very well the sort of effectiveness that humidifying will deliver. And this is based on experiments detailed in the military handbook for the United States Department of Defense, published in 1991. And they conducted experiments that detailed the static voltage of various activities at high and low relative humidities. So if we look at an activity, and all of these activities were at 21 degrees C. So walking across a vinyl floor, when the relative humidity is low, between 10 and 20%, they measured a static voltage of 12,000 volts. But when the humidity increased across the static threshold, again over 45% RH, that static charge utilized those water molecules in the air to distribute to Earth. So that static voltage was reduced down to 250 volts. So that's a 98% reduction in static voltage. Walking across a synthetic carpet at low relative humidity generated a static voltage of 35,000 volts. Again, when humidity was increased across the static threshold, and that static charge, that imbalance of electrons, was allowed to be conducted through the water molecules in the air and distributed to Earth, that static voltage reduced to 1500 volts. That's a reduction of 96%. Something as simple as picking up a polythene bag and measured a static voltage of 20,000 volts. Again, when humidity was increased across the static threshold, and we could distribute that static charge to Earth, that reduced down to 600 volts. That's a 97% reduction in static voltages. So you can see it's incredibly effective when we utilize those water molecules in the air to conduct a static charge to Earth, which is great. But then it leads on to say, oh, okay, we're going to increase relative humidity. But what is relative humidity? So we're going to take a look at that now. And we've got quite a nice model here. And if we imagine this circle of air is this blue circle is a container of air, and it contains about 1 meter cubed of air. But if the absolute humidity, or the amount of water vapor in that air, is 5 grams, then that air will be its maximum capacity. It can't hold any more water. So at 2 degrees C, our 1 meter cube of air containing 5 grams of water vapor is 100% saturated. So 100% relative humidity. But let's say we now increase the air temperature up to 10 degrees C. So the air, when we heat it up, can hold more water. But in this case, we haven't increased the amount of water that we can hold. So the absolute humidity remains the same. But I can hold 50% more water. And in fact, I'm only 50% saturated. And then when we go one step further, let's heat the air up to 20 degrees C. Right here, the air can hold 75% more moisture than it could at 2 degrees C. But I haven't taken any moisture out or put any more moisture in. So the percentage saturation is only 25%. So it's a lot drier. So the percentage saturation changes with air temperature, where the absolute moisture content can remain the same. So how is this manifested in an indoor environment? So here we've got a model of an indoor and an outdoor environment, and you can see that we have a wall here that's representing the difference between inside and outside. On the left-hand side, we've got the indoor condition. On the outdoor side, we've got the outdoor condition. And let's say we have 2 containers of air, one on the inside and one on the outside. Now, at 21 degrees centigrade, and outside it's 50% our relative humidity, we've got a moisture content of 7.8 grams per kilogram of dry air. And on the inside, well, that air is coming from the outside, so we've got exactly the same. We've got 21 degrees C internal temperature. Relative humidity is 50% saturated because we've got 7.8 grams per kilogram dry air. But let's say that outdoor air then gets colder. You can see that air, when it gets to 10 degrees C, is completely saturated. That is kind of okay at this point, because when that air at 10 degrees C saturate comes into the indoor space, it's still got the same absolute moisture content as is required to satisfy our 50% RH at a higher temperature. But let's say the air is going to get even colder outside. Now, as the air gets colder and colder, it can hold less and less moisture. And what happens to that moisture? Well, it falls out of the air. It and that's in the form of condensation, and we see dew forming as the air temperature can no longer hold the moisture content that it once could. But when that air then comes into the inside environment, my temperature is maintained at 21 degrees C, but my absolute moisture content is reduced. So my percentage saturation will fall and I will get dry air. Again, because the moisture content of the air outside is lower, we have to then humidify and put more moisture into the air artificially in the space. So we humidify by either an adiabatic or an isothermal system to increase the moisture content in the space so it's greater than the absolute moisture content of the air outside. So again, as that air drops its temperature, we can't hold as much moisture, it releases the moisture, and so we have to increase the moisture content in the internal space because we don't have enough moisture to satisfy our relative humidity condition. So what does this look like psychometrically? And those of you from the UK that are in engineering will recognize the psychometric chart. And this is the tool that we use to design adiabatic and isothermal humidification systems. And there's quite a lot of data in this chart. So I'll just briefly run through the major elements of the chart. We have the dry bulb temperature in degrees centigrade, starting at -10 and going up to 60 degrees C. But we have another temperature scale on the chart, and that's running diagonally down the chart. And this is our wet bulb temperature. There's 15 degrees C wet bulb, 16, 17, 18, 19, 20 degrees C wet bulb. So we've got these two temperatures, dry bulb and wet bulb, and they relate to the terminology used for the instrument that was used to measure relative humidity in the days before digital instrumentation. We used an instrument called a whirling or a sling hygrometer. And a whirling or a sling hygrometer had two thermometer bulbs on it. One was a dry bulb, that gives you the dry bulb temperature, but one was a wetted bulb, a wet thermometer bulb. So this glass thermometer bulb had a linen wick over it that was attached to a small reservoir of water. And as you slung this thing around in the air, if the air was 100% saturated, then no evaporation could take place and have a cooling effect on the thermometer bulb. So we know if we've got a dry bulb temperature of 20 degrees C and a wet bulb temperature of 14 degrees C, we can read from the chart that the relative humidity is 50% saturated. So there's 50% saturated, 50% relative humidity, 60%, 70, 80, 90, and 100. So I can tell from those two temperatures what the relative humidity is. I can also see what the absolute humidity is, which is how much moisture is in the air, by simply reading it off the side of the chart. So at 20 degrees C dry bulb, 14 degrees C wet bulb, 50% saturated, and 0.0074 kilograms per kilogram of dry air. I can also read the specific volume of air in meters cubed per kilogram. There's 0.85, 0.86, 0.87, and so on meters cubed per kilogram. So at 20 degrees C dry bulb, 14 degrees C wet bulb, 50% RH, and 0.84 meters cubed per kilogram. And then the final bit of the chart is this specific enthalpy, which is running all the way around the chart. And we read this by simply taking our condition, 20 degrees C dry bulb, 50% RH, and drawing a line from this scale intersecting our condition, and then down to the bottom scale, and where the value of the bottom and the top scale is the same, will tell me how much energy is in air at that condition. So psychometrically from the chart, we can plot out what is going to happen when we see a change in environment. So if we have a dry bulb temperature of 21 degrees C, a relative humidity of 50%, and an absolute humidity of 7.8 grams per kilogram of dry air, if we cool that air down, the effect is that I get an increase in relative humidity. There's 50, 60, 70, 80, and so on. But the moisture content remains the same until I get to saturation point. So here I've decreased the temperature by 10.5 degrees and increased the relative humidity by 50%. But then as I cool the air further, let's say I cool the air back to 0 degrees. Let me just run that again for you. We go from 21 at 50 down to 10.5 and then further cool it down to 0 degrees. There we go, down to 0 degrees. You can see that there's a huge difference in absolute moisture content. So the absolute moisture content has reduced by 4 grams. So now we've got air that's saturated at 0 degrees C. And the next thing we have to do, let me just let it catch up, is heat the air up. So as we heat the air back up to 21 degrees C, and we'll see the graphic, run that in just a second. Here we go, we're going to heat that air up back to 21 degrees C. We can see that there's a 21 degrees C increase in temperature, but my relative humidity has fallen to 24%. So that leaves me with a problem because I've got a very dry environment. So I then need to increase the relative humidity to the point where I need to get to. So this is going to plot out an isothermal humidification increase where we increase the relative humidity back up to 50%. So this is what that looks like. We have a start condition where we're controlling an environment at 21 degrees C and 50%. As that air is cooled down at night time, and we take outdoor air, it cools down, gets to its saturation point, gets even colder, and moisture is released. We then have air at 100% saturated and 0 degrees C. And when we heat that air up back to 21 degrees C, we have to then humidify to get us back to 50% RH. So next, we're going to look at some humidification systems. How do we go about humidifying to enable us to get enough water molecules in the air to distribute a static charge to Earth? So the first system that we can see here is an adiabatic spray system. That's the title of the slide. What is an adiabatic spray system? Well, an adiabatic spray system is going to spray a fine mist of water into the air, and it's going to evaporate that water. So it's going to change the state of the liquid from a liquid into a gas. And whenever we change the state of a liquid from a liquid into a gas, that requires energy. So in a direct room application, the energy for running the system, for evaporating that water, is coming from the space. So very often we have machinery in that space where that is giving off a lot of heat. So here's a printer's or a textile firm, or where we've got a lot of machinery that is going to be giving off excess heat. We utilize that heat to change the state of the liquid. And there are many different ways of doing it. You can have a direct spray system, or you can have a compressed air and water system, or just a direct air system that's fan assisted. And these spray systems look quite straightforward. But behind these systems, we have to have a water treatment plant and a pump station. And we'll capture that when we get to the visual. Here we go. Oh, I'm so sorry. My graphic is playing up. So there's a spray system. We're spraying. Here's our pump station. So we have to have a pump station and a water treatment plant to supply clean, high-pressure water to the spray heads. So why do we need water treatment? Well, if we don't have water treatment, all the minerals in the water will stay in the water. And as the water is sprayed out through the nozzle, those minerals will go with the water. But when the water evaporates, those minerals will fall out into the space and we'll get dusting happen. And also, it will clog up the nozzles. So after a period of spraying, those nozzles will start to drip and start to clog. So we have to take the minerals out of the water before we spray it. And here you can see you've got a water softener in these blue canisters. So that's taking the calcium out and replacing it with sodium. That soft water then goes to an RO membrane and then a pump station, which is all contained in a single skid here. And we then pump water to the spray head. So these are great for large industrial applications where you've got a large area and you want to holistically humidify the area to allow all of that area to conduct a static charge to Earth. And the systems typically consist of a series of spray heads. This one is a fan-assisted spray head, so air will be drawn up through the spray head and then assisting the aerosol to be distributed. And again, here you've got a fan that is sending air just underneath the nozzle, and we're spraying water into the space. It's a pretty simple installation. We've got to find somewhere to put the water treatment plant and the control panel, and then we've got to run that high pressure water hose to where it's required in the space. There are different applications as well where we don't want fan assist, where we can just use a system to spray straight into a space. And that may be somewhere where we don't want any electrical motors, so perhaps an ATEX rated area, where we can just spray and then dissipate. And we typically pulse the spray in. We spray a certain amount, then let it distribute, and then spray again. Or on the different types of systems, this particular system is a compressed air and water system. And this uses compressed air to drive air and water through a nozzle. This type of system is typically used where we don't need to worry too much about dust falling into the area. Perhaps it's not so clean an environment. This is quite useful because we can use mains water in a compressed air and water system. So you can have a more efficient water usage system. The nozzles are self-cleaning, so when the demand stops and the compressed air turns off, a diaphragm inside the nozzle will activate and will push a pin through the nozzle and clean any debris out. So they're pretty robust systems. But if you want any localized humidity control, then you would use a high pressure system. So a high pressure system, you can have zonal control and you can feed a certain amount of spray heads from one line that's controlled by a local humidistat. So again, they're pretty simple to install, all of these systems. We just need to make sure that all the services are available. They're low power consumption because again, we're using the energy within the heat in the air to evaporate that water. So it's utilizing waste heat. And again, you can do the whole area, or you can just do a localized humidification with different set points in different places. Controllability is typically plus or minus 5% with these systems, so more than adequate to certainly get you over the static threshold and not raise the humidity above 60–65%. We certainly want a sweet spot between 40 and 60. And of course, one of the other benefits of doing this is that we get evaporative cooling. So we mentioned that as the water evaporates, it's sucking heat energy out of the air. Well, we can utilize that. We can use it for cooling a large area, because for every litre of water that you're evaporating, that is going to suck 680 watts of heat energy out of the air. So you can also get a significant amount of cooling out of a system such as this. But typically these systems are only suitable for duties over 30 kilos an hour, because otherwise they're too big and too expensive when we can utilize a smaller system to generate a smaller load. And typically then we would look at a self-generating direct room steam humidifier. Now these are isothermal humidifiers. So the previous ones that are spraying water into the air are an adiabatic, whereas this is an isothermal. An isothermal meaning that there is no change in temperature, because all of the energy that's used in these is not drawing it from the air around it. It's taken from heating elements that we immerse in water, and we use electricity to heat those heating elements and produce steam at atmospheric pressure. So we would site this unit inside the space, and when we get a demand signal, the cylinder that contains water and heating elements, then our controls will call for the electricity to be pumped through these resistance heaters and will produce steam at atmospheric pressure. And on the top of the unit we have a fan box that, when that senses that steam is being produced, it will run a small fan and just gently blow steam into the space, and that will increase the relative humidity to a set point. So we can get really good control from these units, plus or minus 2% if you're running them on RO water. And they're pretty robust as well. As water is produced, any minerals in the water doesn't travel with the steam, it stays in the cylinder. And those minerals will form scale on those heating elements. So as a heating element expands and contracts, that scale will crack off and then will fall down into the scale collector at the bottom, which periodically can be emptied and replaced. So from a maintenance point of view, they're very easy to handle. So again, we are using more energy here, but on a smaller duty unit, it's easy to control, and we're not running water treatment plants or having that pump station either. So it is very much horses for courses. Now, that's okay for direct room humidification. You may have an existing heating, ventilation and air conditioning plant that you want to utilize to humidify the space. Well, you can do that, but you would generally have to use an isothermal system. So a system that's producing steam at atmospheric pressure. Because if we sprayed water into a duct and let it evaporate, it would suck heat energy out of the air and you'd get unwanted adiabatic cooling. And in fact, you wouldn't be able to maintain the moisture content that's required in the space. By using an isothermal system and integrating that into the system, we don't see a change in temperature in the air going through the duct. So we can control the amount of moisture that's going into the duct and humidify very accurately to the required set point. And you can utilize different sources of energy. You can use a gas-fired unit, or again, we saw a resistive heater unit, or if you've got good water quality, you can use an electrode boiler. Or indeed, you can utilize an existing steam supply. Here you've got a live steam humidifier. That steam would come down into the unit through a pressure reducing valve into this valve body, And when we get a demand signal, the actuator would open a valve inside the valve body, and then steam would be released through these steam injection lances, and that would then evaporate and increase the moisture content in the duct to the required condition. So we can integrate either into an existing HVAC system, or we can do it direct air, but we have to consider the limitations of the capacity of the air in the HVAC system to accommodate the amount of moisture that's required. So what's the process that we follow when you're looking at providing a humidification solution in order to distribute a static charge, or indeed if you have a hygroscopic issue or any other production issue related to humidity? Well, the first thing that we do is we go through a consultation and feasibility strategy. And typically this will be conducted by one of our specialists who would come to site, and they would look at the building and the infrastructure and the energy availability and whether it's feasible to mount a spray system, or indeed look at integrating a system into your existing heating, ventilation and air conditioning system. We also need to look at things like services. Where's the water available? Is there a drain available? What are the power considerations that we have to think about? If we're mounting at high level, what are the maintenance issues? How is it going to be installed? Where is it going to be installed? And how can it be installed where the spray system isn't going to be obstructed by anything at high level? And we may be hanging spray systems from a roof, or we may be hanging them from a column on the side of the building, or indeed a wall. So we need to look at where we can install and how the air movement is going to be affected by that humidification system. And we'll also look at the set points that are involved and what amount of air is involved in humidifying the system up to a set point. So once we've then decided what sort of system is the most suitable for the application, we'll then go on to product sizing and selection. And when we size a humidification system, we do this based on the amount of air that we're humidifying. So we would look at the space and the type of building, and then we'd ascertain an air change rate typical for a building of that size and that amount of how leaky that building is, and how many doors are opening, what's the door opening frequency, and how big are the doors, etc. We'd also look at the amount of mechanical ventilation. How much air are we bringing in or taking out of that space? And how it's done. Because we may have a dusty environment where we've got a dust extraction system, and we need to understand how that's working as well. Because a dust extraction system typically will take air and dust away from the surface or where the dust is being produced, and then typically it will go through a cyclone system where dust is separated, but then air is returned to the space. So we wouldn't need to consider that. But if that air was extracted, then we would. So we need to size the humidification system based on the air exchange rate within the space and the external conditions and the internal conditions required. Once we have that, we can do a duty calculation and a selection. And if we're integrating into an existing HVAC application, we'll be able to then produce a selection and calculate whether we can get enough moisture into the supply air to increase the moisture content in the space to a point where the relative humidity is required. So once we've done that, we would make a proposal based on our findings of our consultation and our sizing and product selection. And then once we have the go-ahead to proceed, it would then be handed over to a project manager who would then go through all of the requirements for the site. It would control the time frame of the installation. It would ensure that the services that are required by both the customer and our equipment are provided for. and confirm location of equipment, and also produce a full scope of works and full scope of works and RAMs and risk assessments and method statements. Then, when installation is completed, you go into the commissioning phase, where we commission the unit to ensure that all the components are installed correctly, and that everything is integrated into an HVAC system correctly, that all the steam pipes are installed correctly, all the water and the electrical fittings are working correctly, and the set points of the units are set correctly, and any integration with an existing building management system is also complete. We then go through a period of training with a customer and then eventual handover to the client. And then finally, of course, there is a service and maintenance schedule, and we service and maintain literally hundreds of humidification systems just across in the UK alone, where we make sure that our customers' production facilities are unaffected by variances in humidity throughout the year by having a preventative maintenance plan in place. Well, thank you for bearing with me through the presentation. Condair provides solutions for 3 technologies. We offer humidification systems, both isothermal and adiabatic, which we can either integrate into an HVAC system or indeed spray directly into the air. We offer dehumidifying systems, so we offer technologies for higher relative humidity, higher temperature applications where we use condensing direct expansion refrigeration systems, or we also get involved in low moisture content applications such as a cryogenics lab where we want very low relative humidities, and we use desiccant technology for that. Or indeed, we have evaporative cooling applications, and here you can see a very large evaporative cooling application in Medina in Saudi Arabia, where we're spraying a huge amount of demineralized water into the air and using these fans to distribute that humidified, cooled air into the space. So once again, thank you so much for bearing with me through the presentation. Please do take the downloads that are available to you, and I'd love to now open it up to ask if we have any questions from our audience.
Hi, Dave.
Hi, Anne.
Right, okay. So, yeah, as always, I've had lots of good questions as I've gone along. So I've just cherry-picked some of them, and others we'll get back to you when we can. So the first one that several people have asked is, does the relative humidity have to be 45%, or is it just above 45%? And also, is there any evidence to back up the fact that it is 45%?
Well, the evidence is we have a lot of customers that we work with, and of course we can't give details of individual cases due to confidentiality. But the science speaks for itself. We gave a demonstration of that in the table from the Military Defence findings. But also, if anybody is interested, you can find various studies from the Society of Electrostatic Discharge that you can use to refer to. But regarding the question about minimum relative humidity, yeah, 45% is really where we want to be as a minimum to allow static to dissipate through the moisture in the air. But as a maximum, we don't really want relative humidity above 60 to 65%, because then we run into airborne pathogens and mold growth if we get a cold area. So we don't want to humidify above that. But we get fantastic transmitting of that imbalance of electrodes as soon as we go over 45%. So typically the sweet spot is 50%, and that allows a swing of plus or minus 5% as well. That controllability is obviously inbuilt into the humidification system.
Great. Dave, next question, quite a good one, is does working at different air pressures and different heights above sea level affect humidity?
It will affect the amount of moisture that's in the air at a given pressure. But we take that into consideration when we're doing a duty calculation. So really, it's the absolute moisture content that is going to change, and that can change in your environmental conditions. So it's always going to be more moisture in the atmosphere in a coastal environment. As we travel further away from the sea, or indeed a higher altitude, then we will see a change in absolute levels. But the change is really the same when we take that air and we move it into an artificially heated environment. So the absolute moisture content is going to remain the same, but the relative humidity is going to decrease as we heat the air up. So yes, it's something that we would take into consideration when we're doing a duty calculation, but it's not something that we take into consideration when we're looking at humidifier set point.
Brilliant, thanks, Dave. Last question, because I'm conscious of time. Everybody else will get back to your questions, very good questions, as soon as we can. But the last question, and I've had several questions about this, is regarding Legionella management with spray systems and cold water systems. What do we do?
That is a great question. Well, Legionella is, or the bacterial name Legionella pneumophilia, is something that we don't want in our water system. So we have various strategies built in to the spray system to prevent that happening. The first one is to make sure that we don't get any stagnation in the system. So when we don't have a demand signal, we will have flush cycles and drain downs within the system. So we'll always be either, if we get a prolonged period of time with no demand signal, we will put fresh water into those lines. So then there's no stagnation. And then we will also blow down those lines, make sure that everything is drained down. Now, it's really important to make sure that these functions are kept turned on at all times. You must never just turn a humidification system off, because it has the inbuilt hygiene strategies that are operated by the system. And you've also got a reverse osmosis water treatment plant. And again, that will have built-in routines that will do drain downs and flush downs to prevent any bacterial growth. And secondly, we also utilize UV treatment, inline water UV treatment, and some systems have silver ion exchange that again counter any bacterial growth. But the biggest thing that we do is making sure that there's no stagnation. We've also always got clean water running through that system. So all the pipe work will have the water, clean water running through them at a regular time. So we don't get any water stagnation in there, and then we don't get the bacterial growth.
Brilliant, Dave. Well, that's it. I've got loads more questions, but I'm just conscious we've gone over the hour now, so we'll leave it there for today.
Well, thank you very much, everybody, and thank you to Ant, and thank you to Duncan for arranging this. Please take the handouts, and once again, thank you all very much for attending, and I hope you got a little bit of something out of giving us your time today. Thank you so much.
Thank you. Thanks.